Okay, so welcome everyone to this public talk connected to the program isogeny-based crypto, which will run here at OIST for another 6 weeks. For this talk, I'm very happy to introduce Professor Steven Galbraith, who's a professor at the University of Auckland, and yeah, he's a man who needs no introduction, a pioneer in the field of elliptic curve crypto, has published books and countless high-impact research papers on the subject, and will today talk to us about card tricks and discrete logarithms. So please take it away, Steven.
Yeah, cool. Thanks very much for the introduction, Jonathan. So I'm very happy to be here at OIST, my first time in Okinawa for this program, and I definitely want to thank OIST for hosting us for the 7 weeks. I'm only here for 2 weeks, but the whole program's running for 7 weeks. And thank you to OIST, and also very much to Jonas, who's been keeping everything under control and helping out a lot. So I'm going to start by presenting this card trick. The cards are laid out here already. And then I'm going to explain how it works. So a lot of the talk's just explaining this trick. It's completely elementary mathematics. And then I'll explain how this relates to something called the Pollard Kangaroo algorithm and discrete logarithms. And then very at the end, I'll connect up a little bit with post-quantum. So this is in theory a general audience talk. Certainly the card trick can be understood by a high school student. The bit about discrete logarithms is best if you know some basic algebra, early university algebra. But apart from that, it's more or less an elementary talk. Okay, so we start with this trick. So what's going on here with these cards? So I've laid out the cards, 52 card, normal European card deck, 52 cards, and we're interested in a process of walking down the deck. And you figure out the way the walk works is you look at if you're sitting on a card, and if that card's got a 5 on it, you go 5 steps along. If that card's got a 7 on it, you go 7 steps along. If it's an ace, you go 1 step. And for the purposes of the standard version of this, if it's a king or a queen or a jack, you go 5 steps down. So you're going to choose a card, and you're going to, whatever the number is, you're going to walk down. But there's a radioactive frog down here. And if you land on the radioactive frog, which I borrowed from the reception, you lose. And I win. But if you can walk down the cards and happily survive to the end, then you win. So for any card trick, it requires some volunteers. And in order to incentivize volunteers, I have a prize. So if you can survive, if you don't land on the radioactive frog, you have 2 possible choices. You could have this very cute little kiwi from New Zealand, which even makes the sound of a kiwi. Listen closely. Oops. No? It's broken already. So that's a beautiful prize. Or if you don't like the kiwi, I also have from New Zealand some very nice chocolate. So have we got any volunteers who want to play against the game? Okay, lots of volunteers. All right, well, I will come down. They can't all be from the pro. We should have at least an oyster volunteer as well. Anyway, okay, well, let's give a hand for our first volunteer. Okay, so you may find it easier to be on this side. I think I'll find it easier to be on this side. So you can start. You have a free choice. You can start with any card along this end of the deck. And just choose one of these, and then we'll walk down. Okay? Yeah. So can I ask? No. You have to avoid this row. You can't start here on the king because no. You have to start at this end.
Okay. Can I ask a question? So since I cannot see, the cards were randomly shuffled.
Yeah, but I will also. I very much appreciate your skepticism. So I will repeat the trick. And I will allow you to shuffle the cards before I repeat the trick. When I try.
Just I don't see them.
Yeah, it's they look random, right? Yeah. So what do you choose a card from down the end?
Go for this jack.
Okay, you're going to go for the jack. All right, so that's 5, right? So let's count together. So we do 5 steps. 1, 2, 3, 4, 5. Now you've landed on a 7. 1, 2, 3, 4, 5, 6, 7. Now 2. 1, 2. Now 7. 1, 2, 3, 4, 5, 6, 7. So king, so 5 steps, 1, 2, 3, 4, 5, 7, 1, 2, 3, 4, 5, 6, 7, 3, 1, 2, no kiwi. I do have as a consolation prize a University of Auckland pen. Okay, we have another volunteer. Another volunteer. Oh, there were more hands earlier. Oh yeah, come down, please. Thank you. I should be asking your name and where you come from, but I'm not a magician, right? So again, you have to choose a card around here. I think you chose one of these jacks, wasn't it? Like, so choose a card from somewhere on this end of the table.
I'll just choose the 4.
Okay, right. So let's count together. So it's a 4. So 1, 2, 3, 4. Did you start on the blackjack?
Yeah.
Okay, well, we already know that's a dead end. I'm going to give you another term because we know the key thing is the whole point of this trick is it's completely determined, right? The course is determined. So since you've ended up after your first step on his starting point, we all know how this ends, right? So let's not do the 4. Okay, so another one other than the 4.
Well, then I guess the objective.
Okay, this is a good one. Okay, so that's a 5. So 1, 2, 3, 4, 5. We've got the queen. 1, 2, 3, 4, 5. A 5. 1, 2, 3, 4, 5. The 7. 1, 2, 3, 4, 5, 6, 7. King. 1, 2, 3, 4, 5. We've been here before. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. That's the frog again. Sorry, it's the University of Auckland pen for you.
Right to the front.
Okay, so I'm going to stop now because I've done pretty well. But I'm going to repeat this again, and we'll have time for another volunteer. So this is a high risk for me because I'm not guaranteed to win this game. I win this about 6 times out of 7. So let me explain to you the mathematics. So the key thing, I said this already, but the really key thing is this is not a random walk. Your only choice is the starting point. You have a free choice of the starting point, but the walk itself is completely deterministic. It's determined by the number of the card you're on. And the really key property, and we've seen it in action. There's a question?
Just for clarification, when you say the starting point is random, would you allow the participant to pick the card?
No, okay. I'm asking, but I'll come back to this point too. I'm asking them to start more or less at this end point. Sure. I mean, if they start after the frog.
No. Just immediately before the frog.
Immediately before the frog, of course. Yeah. Well, this will become more clear as the talk goes on. Yeah. So, but I mean, the key point is the walk itself is deterministic, and it has this property that if at some point you hit a card. And from another starting point, you would hit the same card. The rest of the path is completely determined. So in this case, for example, you hit the 2, you take 2 steps to the 6. You hit the ace, you take 1 step to the 6. You end up at the 6, whether you chose the 2 or the ace. The king, you miss the 6, right? That's clear. And I've got another even more clear visualization here of a sequence of things, and you can work through, and you can see that for many of these starting points, you will end up at the 5, and from then on, all the paths are determined. So that's the key to this trick. So I put the frog on a kind of attracting fixed point, or an attracting point. So it's not a fixed point, an attractor, right? So let me explain the trick, and we will then give a participant another attempt to go. And I promised that I would give this gentleman the honor of shuffling. So please, because we know we can trust you. You can always trust a man with a beard. So what do I do? So when I'm dealing the cards, I start at the first card. So I'm playing this game from the first card, right? So as I deal out, I'm counting from the first card, whatever that number is, I count down, and then whatever card I play there, I count down, whatever. And I put the radioactive frog at the end of that process. And so for sure, if my contestant chooses the first card, for sure they land on the radioactive frog, right? But I'm not telling them to choose the first card. I'm giving them a little bit of choice, and then they're doing this thing. And then the question is, I'm going to explain this, but what's the probability that you end up back? Are you satisfied with that? Cool. All right. So this is how. So now I'm showing you how to do the trick, so you can do it with your kids or your partner before bedtime or whatever you like. So 4. 1, 2, 3, 4. That's a 2. 1, 2. Queen. 1, 2, 3, 4, 5. A 3. 1, 2, 3. A jack. 1, 2, 3, 4, 5. A 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now you see why I did it first before the talk started. A jack, 1, 2, 3, 4, 5. A queen, 1, 2, 3, 4, 5. An 8, 1, 2, 3, 4, 5, 6, 7, 8. An ace. And I know I've got less than 5 cards left, so it really doesn't matter. All right, next volunteer. Who's going to have a crack? Okay, up you come. No, another one. All right, so you cannot choose a card down here. I'm going to insist on the first 10 or so. And obviously you don't choose the first card because you know you're doing it. So choose a card. You can reverse engineer this trick. The 5. All right, so we go through it. 5. So 1, 2, 3, 4, 5. King. 1, 2, 3, 4, 5. What's that? I'm upside down. 9. No. 1, 2, 3, 5, 6, 7, 8, 9. Queen. 1, 2, 3, 4, 5. 4, 1, 2, 3, 4, 10. Oh dear. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4, 1, 2, 3, 4. 4, 1, 2, 3, 4. It's the radioactive frog. I think though, since you're the final volunteer, you get a cute kiwi. Okay, so let's do, so is everyone happy with the trick? You all know how to do it with your friends now? Mm-hmm. Great. So let's do the mathematics. So I want to give you some explanation of where this 6/7 comes from. So first, what's the sort of average length of a jump? So the cards are 1 up to 10, king, queen, jack, and they're all 5. So if you average 1 up to 10 plus 5 plus 5 plus 5, you get something just slightly bigger than 5. So more or less, on average, I'm jumping about 5 steps. So let's visualize it this way. In about every block of 5 cards, I probably landed on one of them, right? That's not exactly how it is, because there's some 10s, there's some aces, you know, but on average, this is back of the envelope type stuff. On average, in about every 5 cards, I've landed on one of them. Mm-hmm. If you land on that card, it's the radioactive frog for you, right? So you have to make sure you don't land on that card. So in every 5 cards, there's 4 that are safe and 1 that's not safe, right? And so from your first choice, but also if you think about your first choice, if you think of that as making a random choice in the next block, that random choice has to be one of the 4 out of 5 safe cards on average. And then your next step in your walk has to be one out of the 4 out of 5 safe cards and so on. So that's what's going on in this formula. There's about 1 over 5.38 is the chance that in any particular window, did you hit the band curve? So 1 minus 1 over 5.38 is the chance that you got lucky and you've escaped that card. And you have to get lucky about 9 point something times if you started up at this end, right? So that's the probability you win, is that you got lucky on your first card, you got lucky on your second card, you got lucky all the way. So that's 1 minus that, and that's 1.37 or so. Now this is not a rigorous calculation. Rigorously analyzing this game is quite complicated. There are multiple papers on it. I don't think there's even a full exact analysis of this. From a probability point of view, it's quite a pain. But anyway, this is pretty close to what happens in practice. So I win with quite high probability, assuming you start up at this end. So you have to do maybe not 9, but 8, or, you know, I need you to have a reasonable number of steps. Obviously, if you start down here, if you only got, you know, you've got, if you start within 5 cards, you've only got like a 1/5 chance of dying, and 4/5 in your favor. Mm-hmm. Any questions about this little analysis? So what about if you start halfway, for example? Well, halfway, the walks are still the same, but you only have to go about half the distance. So instead of the 9.6, on average about 4.8 steps. It's also not quite that, because the frog's also a little bit in as well. But anyway, so you're probably only doing 4 or 5 steps. But even still, even if you start halfway, I've still got about twice as chance of winning as you do. So, you know.
Would you kindly remind me, which card did you place the frog?
You just start with, when you're laying out the game, I mean, the standard way to do the trick is you just start counting from the first card. You could randomize that if you wanted to. But the standard thing is you just start counting at the first card.
Yeah, but the location of the frog.
It's the last card that, like, it's on a king because I don't have 5 cards left. It's the last card you can possibly, right, so I've started at the first card, and I've counted, it was a 4, I counted 4, I looked at that number, I counted, so I've counted the walk, where the walk starting at the first card takes you, and I put the frog on the last card before I run over. Yep, clear? Anyway, it's a fun trick. I mean, it's all right, and you can do this to kids, and it's got some probability theory, and I like it. But even better than that, I mean, this really has algorithmic implications. And so there's this extremely famous paper by John Pollard from 1978, where he uses the Pollard row algorithm, which is even more important, and that's based on the birthday paradox, which is also really cool, but I'm choosing not to speak about the birthday paradox and the Pollard row. I'm talking about the Kangaroo method today, but this paper introduces the row method and the Kangaroo method. It's a really massively influential paper on algorithmic number theory and cryptography. Yeah, this is from 78, and he has a paper from 2000, which is a bit more of sort of an overview, which has got this hilarious title because he also talks about monopoly. There's something about a little bit about playing the monopoly game that ties in with this as well. So this is a nice paper too. And I also want to draw attention, there's something beautiful about this paper, because John Pollard, for much of his career, was a kind of gentleman mathematician. He didn't have an institution. He's not worked as an academic. He worked for a company for a while. But at the time of this paper, he's already just basically living at home. So his affiliation is his home. And look how English this is. Tidmarsh Cottage, Manor Farm Lane. Anyway, and I used to work at a place called Holloway, which is just outside of London and Surrey. And it's not that far. And I got to know John a little bit. And I can tell you, I've been to Tidmarsh Cottage, and it's not quite what you imagine. It's probably a little bit less nice than what you imagine. But anyway, it's still very English. Anyway, I was lucky enough to end up doing some collaboration with John and a student of mine at the time when I was at Royal Holloway. And this paper, I haven't told you the Kangaroo method yet, but anyway, it ties in with all this stuff. And we end up showing that 4 kangaroos is better than 2. But I'm getting ahead of myself because I need to tell you what kangaroos are. But first, I'm going to set the scene a little bit with discrete logs and cryptography. So what are we talking about? What do we do in this community? So cryptography, we obviously try to provide some security services to your communications over the internet. And so authentication is very important. And also encryption and privacy is very important. And all of these things are about mathematics, because if you think about encryption is about performing some operations on data. Data is numbers. So we're doing some mathematical operations, and we want it to be hard for someone to decrypt the message. So you want some mathematical function that you can compute, but it's hard to invert computationally. So this is clearly something about mathematics and complexity theory. So that's what us in our community are doing. We're interested in computational problems that are difficult. We're interested in algorithms for solving computational problems. And so now I'm going to tell you about modular arithmetic, but I suspect that many people in this room already know it. So I apologize for I was expecting, school children and, shopkeepers and all the rest of it. But anyway, I think we know how to do clock arithmetic. If it's 3 hours after 10 p.m., or 11 p.m., it's 2 o'clock. So I assume you'll know this. And anyway, now if you haven't seen modular arithmetic, this is just where you keep all your numbers between, you've got some modulus, which in this case 29, and you keep all your numbers between 0 and 28. And whenever you do any kind of algebraic operations, you subtract multiples of 29 so that your numbers stay between 0 and 28. So I've computed the powers of 2 modulo 29 by just each time I'm doubling the value before, and if I double and I go bigger than 29, I subtract 29, right? So that's all that modular arithmetic is. And this is a great way to get a sort of algebraic system that is finite. So what we want in cryptography, cryptography doesn't like the infinite. Computers don't like the infinite. No, we don't like to do cryptography over the real numbers. We like to do cryptography with finite discrete objects. So getting systems like this where this is the integers modulo p, where you've got something where you can do algebraic operations, addition, multiplication, but everything stays contained. There's no rounding errors. Everything's got a fixed representation size on the computer. This is what you want for cryptography. We don't work modulo 29. I thought I'd find a prime. So here's a two. If you really wanted to do mod P, discrete logs mod P, you'd probably look at something like 2000 bits these days, and that's apparently a prime number. But I don't know 1900 bits of pi, so I can't tell you what this number really is. But anyway, this is the sort of size that one would do if one was doing modular arithmetic mod P for their Diffie-Hellman key exchange. Now, all of us in this room use, or all of us in the program use elliptic curves, but I don't want to talk about elliptic curves today. So anyway, so what this leads to is this computational problem, which is where I take some number G, so this is 2 in my example, and I take some prime, it was 29 or that other number, and I compute 2 to the power something, modulo that prime, but the something is the secret. So I can efficiently compute 2 to the power of a very large number, modulo another very large number. And the conjecture is, with classical computing, it's hard for you to work out what number I use. So this is the discrete log problem. Okay, so it's called logarithms because it's a bit like, you know, if you're given e to the x, how do you find x? Well, you just apply the log function, right? So this is like a discrete version this is the discrete version of exponentiation, and so inverting it is a discrete version of taking logarithms. So so in this case, like G is 2, P is some prime, and you're given some number, some integer between 0 and P minus 1. That's public, and the secret information is the exponent that was used. Any questions about that? Is that somehow clear what's going on with this problem? And there's this incredibly beautiful and incredibly simple idea. It's due to Diffie and Hellman from a paper from 1977 or 1978. And so the idea is there are two people communicating over the internet or some untrusted, it wasn't the internet in 1978, but Alice and Bob, they want to agree on some random thing that only they will know. So they're not communicating a message yet, they're just trying to agree on some random stuff. And so the idea is Alice chooses some secret number, little a, and she computes g to the power a. So Alice can compute that arrow, and Bob chooses some secret number b and computes g to the power b. So Bob computes that arrow, and then Alice sends g to this number g to the a to Bob. Bob sends g to the b to Alice, and then Alice can exponentiate this value to the power a. So she computes this arrow, and Bob can take the number he gets from Alice and raise it to the power b, and g to the AB is the same as g to the BA, so they agree on the same thing. And this is incredibly elementary mathematics, but it's a wonderfully powerful idea in cryptography that people have just created the most extraordinarily complicated crypto systems out of this simple, very simple algebraic thing. Any questions about that? Okay, I've got plenty of time. I'm going to finish early, I think. All right, so, here's an example of, I mean, you're using this all the time, whether you know it or not.
So actually, I have a question.
Mm-hmm.
In this key exchange, is this with the modulus or without the modulus?
Yeah, so everything is mod P. So yeah, so the kind of the system, the starting value G and the prime P, these are kind of fixed that everyone's using. And so this is definitely G to the A mod P. Okay. And that's G to the B mod P, and the shared secret is G to the AB mod P. Definitely, yeah, okay. yeah. So because we want to work with these kind of fixed size object. Okay. Yeah, good question. Any other questions? Yeah, so here's just that if you go to a website and you click on the padlock and try and find some information, you'll end up with something like this. So this is some website I looked at, and it's got this thing TLS. ECDHE, so this means elliptic curve Diffie-Hellman. And then RSA signatures, whatever. So I will tell you how this exact card trick became Pollard's algorithm. It's exactly this card trick. Okay, so this card trick becomes an algorithm for the discrete log problem, and it's useful in a particular setting. So I'm not going to explain too much about the motivation, but it's particularly the setting where I've got a discrete log problem. So I've got there's some g, and there's some g to the a mod p. And I'm particularly interested in the case where the a is somehow in some bounded, so it might not be the full, might be not all the way to p minus 1. So if a is going all the way between 0 and p minus 1, then you want to use the Pollard row method. But if a is a bit smaller, which sometimes happens in some applications, then this is the algorithm you want to use, the Kangaroo method. So the idea, kangaroos are a bit like the jumps in the cards. Kangaroos are going to go a relatively short distance. They're not big jumps that go all the way around the backwards and forwards. They're going to go small jumps, and they're going to go in one direction. So that's what kangaroos are. They're not. They're pretty close to frogs. They jump along like that. And also in Pollard's paper, he talks about this. The kangaroo, the jump of the kangaroo depends only on sort of the landscape on which he's standing. So somehow the jump's going to depend on just where you are in some sense. That's kind of right. So anyway, it's going to be based on the Kruskal trick. And so what we're going to be generating is we're going to be generating a sequence of things, but we're actually generating two sequences, and it's a little bit confusing. We're generating a sequence of integers AI and a sequence of group elements, or integers mod p, ui. And it's really, the kangaroos are really an exponent. The AIs are integers, so we can think of them as being well ordered in a linear way. 1, 2, 3, 4, 5, 6, 7, 8 is the integers. And so it's the AIs are going to be increasing by small jumps. The UIs, which are the group elements, they're just going to look like some random sequence. They're just jumping around the group. But it's the exponents that are going to be moving. So the kangaroos are really living in the exponent. So let me just jump straight to the algorithm. So we choose some set S. They're just sort of random. These are the jump lengths. So if you like, these are the numbers 1 up to 10. These are the possible jumps I'm making at any point. And we have some way of choosing for any group element, which jump do I take? And it should be a deterministic method, because I want to make sure if I come back to that group element, I take the same jump again. So I've got this hash function h, which is just, and I've basically partitioned into k things. You can think of these as the 13 different types of card. This was the game with k equals 13. So I've got 13 different types of card, and I've got some deterministic way of identifying a card to a group element. And for each of these different cards, I've got a particular jump length. And I start with the first card, with g to the power 1. And I run this walk where for each group element, I hash it, take the appropriate jump, but the jump is in the exponent. So I start with the first card, which is g to the power 1. So A1, the exponent is 1. And then to get the next group element, I jump by g to the s, and it's the same as adding A1 plus s, right? So I've got the little exponents are being added by the length of the jump, and that corresponds to the group element multiplied by g to the power of that value. So the group elements are changing by multiplying by g to the something, and the exponents are the somethings are getting added up. So like I say, the kangaroos are in the exponent. So I start at the first card, run the walk, and every now and then, I put a radioactive frog on one of the cards. I've got lots of frogs. These are called distinguished points. Not very important, but this is the contribution of Van Orthotten. I keep going. And then in parallel, this is called the tame kangaroo. And in parallel, I have the, I've kind of said that. So in parallel, I have the wild kangaroo. And this is the kangaroo that starts at H. Remember, H is G to the A, and I don't know A. I'm trying to find out A. So H is the card that you chose, right? It's G to the power A for some A. I don't know what it is. But I run the same walk. So again, in the exponent, this is the eighth card, if you like. I don't know what A is, but I start adding kangaroos, and I start running the walk down. So I'm going to do some walk from this card that's going along, and I keep track of the things I'm adding. So I don't know the discrete log of this. This is G to the power unknown. But when I do the walk, I'm going to be always adding on G to the power known things. and I'm going to keep track of them with BIs. So in this case, VI is H times G to the BI, right? The tame kangaroo was always G to the AI. The wild kangaroo is H times G to the BI. So again, I start with my wild kangaroo and I do the walk, and every now and then I hit a distinguished point and put a radioactive frog on it. And at some point, I'm going to put a radioactive frog on top of another radioactive frog. And I go, aha, I've been here before. So at that point, where the tame kangaroo and the wild kangaroo have landed on the same distinguished point, I terminate the algorithm. I've got a collision. And that means that I've got some G to the A being equal to H times G to the B. And so I've solved the problem. All right. This is the kangaroo method. So I did that actually quicker than I needed to. I'm sorry about that. So I don't know if there's any questions. Let me just go back. Let me go back to the tame kangaroo again, and let me just emphasize it again from the card point of view. So the jumps, the SIs are like how far down the track I'm going. The AI is the sum of all those numbers. So it's actually how far down, essentially which card I'm at. I was at the first card, I had 4, I was at the 5th card, whatever. So the AI is going down here. And the U's somehow don't really have an analog in the card game. And the wild one, the wild kangaroo, there was some B. Someone pointed at one of these cards and I was blind. I don't know which card they're pointing at, but I'm again going to keep track of how much I've added to that card. And so at some point when both hit the same frog, I knew this one was so many steps, and this one was the unknown value plus so many steps. So the difference is the unknown value. Does that help explain the algorithm? Any questions at all? Yes?
Not fully a question, just a remark about analogies. Instead of 2 kangaroos jumping around and meeting next to a frog, I would suggest a kangaroo hunting a frog.
Well, it's a bit more gory than that in the paper. I wanted to spare you the details, but since you've asked the question, he actually digs a hole and covers it over with leaves. And so the kangaroo actually falls in a trap. So, it's actually pretty nasty business. Yeah. I mean, as a New Zealander, that's okay. I don't mind if Australians suffer. Okay, so this is exactly it. So it really comes from this card trick. And in fact, the Pollard writes that so Martin Gardner had a column. Which magazine was that? Scientific American, right? So Martin Gardner had this column in Scientific American, and the issue which presented the RSA algorithm, which was kind of the first public release of the RSA algorithm that was in Martin Gardner's column. That it was written in the column before the paper was published showing RSA. And the same, Pollard writes that the same issue of Scientific American, where he got interested in these kind of questions, had some article about kangaroos. I haven't verified whether that's true or not, but anyway, it's a good story. Okay, this is all great. Discrete logs. Yeah, and I should say, I haven't really given the punchline. There was a square root n somewhere I said square root of n, and the point is the jumps are of size square root of n, and you've got to cover an interval of at least n. So you need to do about square root of n steps. So this algorithm is some kind of algorithm that takes about square root of n steps, which is pretty good, but very much still exponential time. So this algorithm is an exponential time algorithm. It's not breaking any crypto systems anytime soon. So this discrete log is great. We're using it today to protect our internet transactions. Everything's good, except for the physicists who had this great idea, well, and mathematicians. I mean, Manin had this idea as well, had this idea of a quantum computer. And Peter Shaw showed that with a quantum computer, you can solve this discrete log problem. You don't need to do kangaroos. You can solve the discrete log problem in polynomial time with a sufficiently general purpose quantum computer. So that's very unfortunate for discrete logs. And for those of us who spent a lot of time studying these kind of algorithms, it's disappointing. You think, oh, I'm going to have to rebrand myself. What am I going to do for my research now that we have algorithms? And I mean, the point is that for a long time, nobody was at all concerned about this. I mean, I got into cryptography after 1994. So in the year 2000, people were very happily writing papers about discrete logs, studying these algorithms, and nobody was caring about quantum computers. And then, I don't know, sometime between 2010 and 2015, people started to get a bit more concerned about quantum computers. And oh yeah, this is sorry. Before I interrupt my story, it's time to play my favorite game: quantum computer or microbrewery. Okay, which was which? Which is which? Okay, you may or may not know that IBM is a company that makes computing equipment, and you probably don't know that Garage Project is a microbrewery in Wellington, New Zealand. But anyway, this is actually really old. So these are old slides. Yeah. So anyway, quantum computers. So luckily, there's a new field has been created, and that's what this program at OIST is part of. There's a new field called post-quantum cryptography. So what is post-quantum cryptography? The key point is we are interested in things that you can do on your phone. Not everything isogenists are doing can do on your phone, but we're trying to get it to the point where you can do it on your phone. So we want stuff that runs on current hardware, current communication networks, doesn't require rebuild, doesn't need quantum computers, doesn't need quantum channels of communication, doesn't need any new hardware, it'll run on existing hardware and existing software, but is secure against an attacker with a quantum computer. So that's what we're interested in. And it's totally a thing. You are already able to use it if you want to, and you may even have used it without even knowing it. If you've got Signal, you've used it. If you're using certain browsers, you're potentially using it, assuming the server you're connecting to is also supporting it. So it's real. It's happened. We have international standards, and Peter's going to talk more about this next week. So I mean that's really cool. So that's what we're doing. So I don't work on discrete logs anymore. I work on post-quantum cryptography, but I do want to end with a story. So in this is a terrible picture, but this is supposed to be an isogeny graph. So never mind what this is. But anyway, this is the kind of thing that we study these days. And for a long time, I was trying to do something like Pollard Kangaroo method on isogeny graphs. And I was getting nowhere. But I really spent a long time on it. I mean, I thought about it on and off for years, and I got like a large LaTeX document and all sorts of stuff. And I was trying to do some kind of thing where you would start, for those who know SIDH, you sort of start at both things, you take random walks at some point, they collide, and you had this, I was trying to, it seemed like a good idea. But there were all these obstructions. I couldn't get it to work. I was going nowhere. But there's this funny story about research. Sometimes a dead end ends up leading you somewhere. So because I've been thinking about that problem so much, I started to be thinking about other questions, and eventually led to this paper with Christina Delft, who was a PhD student in Oldenburg who visited the University of Auckland for 6 months. And that was after me working on this for several years, trying to get this damn card trick to work for isogenies, we were sort of primed to think about these questions. And this has ended up being a quite influential paper that I'm very pleased with. So, this is the thing. Sometimes you're doing research and you're banging your head against a wall and it's a dead end, but it opens another door because it sort of primes you to think about certain problems in a certain way. All right, that's all. Thank you very much.
Thank you very much, Steven. Are there any questions?
If you get a really good question, you get some New Zealand chocolate. Okay, you can go to the back.
I'm not running for the chocolate. So this card game phenomenon and hence the Kangaroo algorithm are linear phenomena, like they move in just one direction. Naturally, one can think of the two-dimensional or higher dimensional counterparts. Have you considered?
Yeah, totally. So the PhD student I mentioned, Ruprai, his PhD was mostly about higher dimensional discrete log algorithms, and it was building on work by Gaudry and Schost. There's a paper by Gaudry and Schost about high dimensional things, and really this is an entirely one-dimensional. I couldn't even get this to work on a tree, and this definitely doesn't work in 2 dimensions. So you're really back to kind of more birthday paradox type methods as soon as you go to 2 dimensions. I don't know any way to. So this is very much as linear. linear idea. And like I say, I thought about it a lot when Raman Darupai was doing his PhD, whether we could do some kind of high-dimensional kangaroo method and for this particular sort of Godry-Schoss type problem, and we got nowhere. And like I say, I tried to do something on trees, and I got nowhere.
Even for dimension 2, they don't have.
Even for dimension 2, yeah, it's really the analysis is very close to the birthday paradox. So this kind of formula, the way you do the calculations, this 1 minus 1 over this is very similar to the birthday. In the birthday paradox, this is the idea that if you have 23 people in a room, you've got at least 50% chance that 2 of them have the same birthday. And the analysis is exactly the same. You basically say, well, the first person, his birthday is, or his or her birthday is different to everyone else. Second person, they just have to have a different birthday to that person. So that's 1 minus 1 over 365. The next person has to avoid both those 2 birthdays. So it's 1 minus 2 over 365. And so you go, and then you end up with, instead of this thing to a power, you end up with a 1 minus 1 over 365 times 1 minus 2 over 365 times 1 minus 3, up to 23. And then you do some little approximation by approximating these by e to the minus something. You do a sum, then you end up getting the answer out. So it's a very similar calculation to the birthday paradox. But the birthday paradox generalizes very happily to all sorts of things. I can do birthday paradox for discrete log algorithms in 3 dimensions, no problem at all. But this analysis where it's the 1 minus a fixed probability to the number seems to be just a one-dimensional thing. Maybe there's something I don't know. But you could definitely get a chocolate for that.
Actually, I think there is like a paper by Anna Ledevea and Ben Smith about like 2D kangaroos and the application for seaside. I don't know the details. There are a lot of caveats, and you cannot apply this like readily. But apparently, they managed to still use it.
Yeah, you're right. I did see that at some point, and I probably should look at that more closely. But yeah, whether it's really,
it was modified.
Yeah, and I mean, it always comes down. I mean, to my mind, it comes down to what you call a kangaroo. You can call anything a kangaroo. It comes down to whether you're using the birthday paradox to analyze the probability, or whether you're using this thing. And if it's the birthday paradox, it's not really a kangaroo. It's just a birthday. It's just Pollard row. Oh yeah.
You mentioned that 4 kangaroos are better than 2. So I wanted to ask, are the extra 2 kangaroos also like tame and wild, or are they new types of kangaroos that you're including in this?
Good question. Yeah. So I mean, this is all about the constants on the front. So in fact, the best way to do the algorithm, I lied when I told you the kangaroo algorithm, because you actually start the tame kangaroo in the middle. You don't start the tame kangaroo at one end. You start the tame kangaroo in the middle, because the wild kangaroo might be all the way up here. And there's no point starting the tame kangaroo down there if you have to go all the way here before you can even hope to get it. So the best thing to do is you start the tame kangaroo in the middle, and then you have a kangaroo. And then the analysis, you think about the front kangaroo and the back kangaroo, and what's the expected distance between them. It comes down to a sort of a parity thing, a sort of dividing the set, so that you can do a three kangaroo version where you say, well, I'm going to have 1 kangaroo going on the odd steps and 1 kangaroo going on the even steps, and I don't know whether the wild one is even or odd, but I'll just let that run, and it's going to hit either the even or odd one, and this allows you to tweak the parameters and get some small speed up. And then the wild is basically riffing on that a little bit. It's about well, and it's also about whether you start all your kangaroos in the middle or whether you start some kangaroos spread around. So it's adjusting where the kangaroos are starting, what the jump lengths are, things like that. And I'm slightly embarrassed to say, it's so long ago I can't actually remember exactly whether it's 3 tames and 1 wild, or 2 wilds and 2 tame. I can't remember. Yeah. Yes.
Yeah, very nice talk. So I'm not from the field, so maybe my question is, Nate, it's a general question about this post-quantum cryptography field. So I understand that the set of existing quantum algorithms is still a work in progress. There are things being developed. So when you say that these algorithms are resistant against attack, are you talking about existing algorithms?
Yeah.
Or can you prove that it's impossible for a quantum algorithm to crack them? what is the
Yes, great question. This is always exactly the right question to ask, and I usually get this. So the whole of cryptography is based on assumptions. So we do not have, I mean, the computer science is still somehow a field in its infancy, because the PNP question is unsettled. So we don't know that there exist any hard problems. And cryptography requires hard problems. So until at the very least the PNP question is settled, cryptography is always going to be based on assumptions. And but the kind of the stuff that leads to practical crypto systems is even much worse than that. So the things we've been relying on now, factoring, for example, discrete logs. I mean, these are nothing like NP hard problems. They're definitely easier than we would think of them as easier than hard problems. So we're always living in a state of complete uncertainty as to how hard our problems is, and all we have is the fact that people have studied these problems for some significant time and not broken them. And that's where we are with post-quantum. We've got all the various bits of mathematics that are being used for post-quantum cryptography, and some of them have not been studied that much. And at any moment, some new algorithm could be found. And we all in this community remember vividly when one of our problems was really suddenly destroyed. Luciano's here, so is he here? Yeah, blame him. So yeah, at any moment, there could be some new discovery, even with a classical algorithm, let alone a quantum. But again, as you say, with quantum computers as well, at any point, someone could come up with a new quantum algorithm, and maybe some of our assumptions would be broken.
Thanks.
Yeah, I have a question. I hope it's not too vague, but I do want to win a bar of chocolate. So since you're from Auckland, which has, I think, a famous group in algorithmic randomness, I guess you know.
Yes.
Down here in Hirschfeld that alluded.
Yes.
So your talk is both about algorithms and about randomness, but I don't see algorithmic randomness or Komagorov complexity, although that is, especially Kaludi showed, related to coding, decoding, Shannon entropy, all of that must be there.
Yeah, that's good. Yes, I do know the community you're talking about and the kind of things they study. Certainly, cryptography relies enormously on randomness. You more or less cannot do cryptography without randomness. Even the most basic types of cryptography. If you think about your cipher machines from the 1940s, for example, you have to set random settings at the start of the day. Well, someone had to come up with a bunch of a code book full of random settings, right? And they had to be random if they were predictable. So randomness is absolutely necessary in cryptography. And I think part of the reason why we're not using any of that hard stuff is that we keep ourselves very much in the finite realm. So like I said, we choose a prime of a certain size, and then as far as randomness is concerned, we have uniform distributions on finite sets. So my understanding of a lot of this other stuff is it's really talking about things like randomness, but what is a random real number, these kind of things, right? This is where you need these kind of algorithmic randomness questions to understand beyond the countable.
I mean, there's now asymptotics.
Oh, there's you can do asymptotics, but we can also do even concrete, right? And I mean, we're really interested in what's the running time of this algorithm on this particular instance. I mean, the asymptotics are absolutely valuable, and we need them, but we need even more than the asymptotics. We need, what people do is they really run the algorithm and draw points and fit curves through them. And, yeah, whereas this other stuff, at least that's my understanding, is a lot of this Martin Lerf and Kolmogorov stuff. This is really about trying to put notions of randomness on uncountable sets, for example. And we're not interested in we're interested in the finite. But it's such a good question. You get a choice of sea salt, caramel, brittle, raspberry, strawberry, or manuka, pear, honey, and pear.
Aim has been achieved. This one looks fantastic. I have a bonus question as a beginner. So I'm not in this field, but in Diffie-Hellman, is the prime P supposed to be very large?
Yeah, very large. Exactly, like 2,000 bits or something. Yeah, huge. Exactly. Oh, Peter.
I have a question about. So here, everything is about runtime, but actually, memory is. Really important. So basically, these distinguished points, right? They are
How many frogs did I have to get 3D printed? Yeah,
yes.
Exactly. Yeah.
So I wonder if because I mean, many of these birthday type or I guess Kangaroo type algorithms, you have this type of square root complexity, but sometimes the memory issue is there and you can't get it going. So is it well understood when you can have these distinguished points and get polynomial memory?
Yeah. So basically, the distinguished point is a parameter you tune. So you decide for yourself what your definition of distinguished point is, and you choose that basically depending. I mean, essentially, what's happening is you're running this walk. We saw this with the actual trick. I put the frog on the last card. People did their walk, but sometimes you'll know. Sometimes I already I revealed that I knew the person was doomed already. Because I could remember that that card had been the card that had come up, right? So sometimes you can tell even in a few steps that this walk is doomed. The collision's already been made. But if I'm running this algorithm parallel, right, or distributed, I've got one processor that's run one of these walks, and another processor that's running this walk. I mean, this processor has no idea which elements these ones have. So every now and then we're going to put down a frog, and every now and then we're going to send that off to the server, and the server is going to be recording which walks landed on these frogs. And so the more apart the frogs are, the fewer points are being sent to the server, the more work each distributed process has to do until they get a distinguished point, and the server has to store fewer points. If I make the points more common, and it's my choice, I define what is a distinguished point. It's just something based on the bit representation or whatever. So if I have more distinguished points, the servers are doing less work to get distinguished points. The server's storing more of them, and the point is the clients. When the collision they're not having to do much work beyond the collision. They don't know when they've collided, because they're sending the points often. They don't have to do much work beyond the collision before it gets detected. Whereas if the points are far apart, the clients are doing more work. So it's just a parameter you choose to trade off the storage you've got available, how much extra work you want the clients to be doing.
But can you still get the square root of n complexity here with polynomially many frogs?
Polynomially many, yeah. So basically, you set it's what we call theta. So you set theta, the probability of the distinguished point. The storage is theta times root n. So if you want polynomial, that would be polynomial over root n. And then it's basically a question of how well does it parallelize. So the total time is still root n. I mean, if you're just doing it with two processes and you're happy for both processes to run root n time, you can just put one frog way down far enough, and it will more or less do it. But if you want to parallelize to thousands of processes, and you want each processor to be root n over 1,000, if you want to get the full speed up from the parallelization, so each processor is doing no more than root n over the number of processes, then you need to make sure the distinguished points are common enough that, I mean, the last thing you want is a processor spending all this time and then never hitting a distinguished point, right? Because then all that work's not been recorded. So there's some little parameter there. But I think if you say that the number of processors is polynomial, which is a reasonable assumption, then the storage is also polynomial. So the storage is probably something like, some large number times the number of processes or something. I probably could have answered that quicker.
It's more or less a question on the asymptotic. You said this, this has square root of n complexity more or less, and also Pollard square root. I was wondering why you were so interested in generalizing this to two-dimension when you already have Pollard that generalizes two dimensions.
Yeah. So it's this Gogri-Schost. The paper originally comes up in point counting, and it's when you've done point counting on high dimensional abelian varieties. So if you're doing elliptic curve point counting, you get some information modulo small primes. And the group order is in some Hasse interval, and so you know the group order modulo a bunch of small primes, and maybe you finish off the computation with some kind of baby step, giant step, or Pollard type method. And now if you want to do this in higher dimensions, you're doing a Scophe type algorithm. You've got a zeta function with several coefficients that are unknown. You get information about these coefficients modulo L. They're different sizes, so you've sort of constrained this thing into some kind of box, which is rectangular, and then you want to do some kind of random walk algorithm which goes within this box. And And then it's just a matter of, what's the way of setting this thing up? And there's this Grotry-Shostak algorithm does this, and they used it for point counting in genus 2. And it's based on the birthday paradox. It's fine. So it was more just an academic curiosity as to would there be a Kangaroo type version for that? Because there's some issues with implementing these things, and so I was interested in looking at all sorts of different ways to maybe improve. We did end up we actually did. I have a couple of papers that improve the Grotry-Shostak algorithm, and by doing all sorts of rather strange things. I don't want to talk about now, but anyway, if you're really interested, you can look at those papers. But they're not that interesting, but it was fun to do at the time. But yeah, at the end, they're all based on the birthday paradox.
I thought that this N wasn't the size of the group, but like a promise on the size of the secret. So wouldn't Pollard row run? It would depend on the group size rather than. Yeah, isn't that the misunderstood?
Yeah. So Pollard row. If all your promises is that the discrete log is somewhere between 0 and p-1, then Pollard row is the better method. The complexity of Pollard row is square root pi n over 2, which is about 1.2 root n, and this Kangaroo method is about 2 root n. So 1.2 root n is better than 2 root n. It's just constants, but So if you're really in the whole group, you use Pollard row. But as soon as you're less than about, if your n is down to like certainly p over 10 or something, you're better off already with the Kangaroo method. But there's definitely, there's papers. If you want to find out the papers that talk about discrete log at an interval, you just look at the introduction to my paper where we work on it. There's motivation for this problem because of this pseudo-random number generator and the scheme by so-and-so, whatever. So there are published schemes. Obviously not actually, I don't think anyone's implemented it in the real world, but there are published schemes where naturally people are choosing their discrete logs in some interval. And then this is very similar to the question with C-side, right? Do you choose, if you're doing the key exchange, do you really worry about whether the product of Powell's primes actually covers the class group, or is it close enough? It's the kind of thing that comes up in cryptography sometimes. Do you really need the uniform distribution, or is some sufficiently large entropy set good enough? And so these kind of algorithms come up when you want to cryptanalyze that sort of question.
Am I allowed to ask?
You're allowed to ask a question, but then we probably wanted to wrap it up.
Yeah, let's continue a bit on this. So in dimension 1, of course, you get the square root of the key space. But as far as I know, these like Grotry-Shostak algorithms and so on, they really are exponential in the dimension as well, right? So for instance, C-side, the best isn't the square root of the key space. But is there any hope to get really square root of the key space, or?
No, there's no guarantee. There's basically, the first question is, can you do something like baby step, giant step, right? So if you confronted with a new problem, first thing you should think about is there's some kind of involves searching some space. First thing you should think about is a very basic time memory trade-off. So baby step, giant step, and if you can't even do that, then tough luck. Certainly C-side, that's easy. It's easier to do a baby step, giant step type thing. And then the next thing you think is, is there a low memory version? And yeah, it's not at all clear there is. And a more elementary example of this is there's something called the low Hamming weight discrete log. So in the low Hamming weight, you're given g and g to the a, and a is an integer between 0 and p-1 that's chosen to have Hamming weight k, where k is some number that's significantly smaller than log p. Right, so you've chosen an exponent at random, and its Hamming weight is. So you can do a time memory trade-off for that, where you basically say, well, let's just assume that A is an integer of low Hamming weight. So you look at it in binary and you say, well, let's just hope half the ones are in this first half and half the ones are in the second half, and you can do a baby step, giant step algorithm where you take all the g to the somethings where they have weight over 2 and whatever, and you can sort of random self-reduce a little bit. And anyway, so there's some kind of baby step, giant step algorithms for low Hamming weight discrete log, but we don't know a square root time low storage method for that problem, and that's a problem that people have looked at for 20 years with no luck. Alex May has a paper on that, for example. Oh, well, I think we're going to wrap up, but okay, one last question. No, it's okay.
Can I try to be quick? From the beginning, when you wanted to describe your Kangaroo algorithm, you started with the card games, but among the cards, there were Jack, Queen, and King.
Yeah.
That you decided to label as 5.
Yes.
You could have chosen different numbers, you would have already skewed your game, and then the outcome. In the Kangaroo algorithm, are there also elements of kind of decision that can kind of skew your algorithm when you decide accordingly?
It's a really good question. It's almost the question I thought you were going to ask. So one of the questions that sometimes gets asked when I play this game is, was I cheating by setting the king, queen, and jack to be 5, right? Because I mean, I should have said the jack was 11 and the queen was 12 and the king was 13. Does the trick still work? So that's the question I thought you were going to ask, because I have a slide for that. So the answer is it does work, but not as well. So the reason why you want to keep to the 5s is that really I have a much less chance of having to give away a Kiwi. But in terms of the question you actually asked, which is how should you choose these jumps? Yeah, I mean you definitely don't want kind of trivial cycles among them. So I don't want to have, like, it's not great if I have, this jump plus this jump equals this jump plus this jump, because you really want this to be kind of the jumps to behave as randomly as possible. So any kind of sort of small kind of dependency that random jumps wouldn't satisfy is bad. So, but equally something like powers of 2, which sounds like you guarantee there weren't any small collisions, that's not great either, because they're sort of just, some of them are far too big and some of them are far too small. So the heuristic is that you choose your jumps randomly in a certain way. But that also does remind me of an interesting question, which is actually rigorously analyzing, informally analyzing these algorithms is really hard. And there are long, deep, complicated papers understanding Pollard row and Pollard Kangaroo. And there's things like, what is actually the probability space we're working with? You want to randomize over the problem instance, but you want to randomize over things like, for example, the choice of the jumps. And all these things have to be handled very delicately in the theoretical analysis. So you're on the right track. It's this kind of stuff, to a certain extent in the practical implementation, but also in the theoretical analysis, you really do have to think about a little bit how it's done. You don't want to think about the jumps as being, I always use the same jumps. They really should be randomly chosen to get the algorithm to behave like it should. But you randomly choose them once at the beginning, and then obviously the walks have this deterministic nature, so you have to stick with that choice. But if at a certain point nothing happened, you might want to restart the whole thing. Fresh random jumps. All right, I think we should stop there. But yes, thanks.